So, last time I was talking about development of rate equation from a mechanism. So, the mechanism is to be hypothesized, that is the first thing, and that hypothesis is based on the experimental results. You have to do some experiments or some based on the fundamentals of the bond theory, that which surface or what are the type of surfaces, metal surfaces, and then how the molecule gas A, or depending upon the molecular property of that reactant species, it will adsorb on the surface, right. So, rate of adsorption or just sticking probability or microkinetics. So, the at the micro or molecular level, that is the molecular dynamics of these molecules or kinetics need to be understood first, that is the first thing, and once you know that, then one can just suggest a mechanism which is based on certain hypothesis, based on the bond theory, and based on certain principle of the reaction engineering or metal type of the gaseous species to electronic configuration of the molecule, what we were discussing during the catalytic synthesis, preparation, characterization, and the properties of the catalytic material. So, all these depends, and based on those understanding you need to identify or devise a mechanism. So, we are talking about two kind of mechanism for developing a rate, and there can be other also different researchers have provided some other kind of mechanism also. So, basically these are what I told last time is a Langmuir Hinshelwood type approach, and the second one I was talking a Allais-Riedel type mechanism. So, in the Allais-Riedel type mechanism I told you that one species is present in the gas phase. So, that is a gas phase reactant. So, A, which is a gas molecule, reacts with the reactant, that is the A reactant adsorbs on the surface of a catalyst, which is active site of the catalyst. So, adsorbed A, and then adsorbed A reacts with another gaseous species, which is your B, and transform it into a product P. So, overall reaction is A plus B transforms to P. So, but A only adsorbs on the surface of the solid, B does not adsorb, right. So, that is depending upon their molecular theory or molecular kinetics or mechanism of the properties of the gas and the catalyst material. So, that is to be understood based on some mechanism, that is the molecular reaction aspects of fundamentals of those based on bond theory, as I said, energy related to the making a chemisorption. So, it should not be very strong, it should not be very weak, and there should be some optimum concentration of that species, and then based on the adsorption principle this will happen, right. So, one can postulate both mechanism also, that A adsorbs, B adsorbs, and then react, which will be a Langmuir type mechanism, and then finally, you have to just do some modeling. So, model discrimination and parameter estimation, and that is what the overall purpose of this doing the kinetics and understanding the reaction mechanism that helps to commercialize the reactor or size a reactor designing, right. So, this adsorbed species reacts with the gas here, in this case Allais-Riedel mechanism, and transform into a product. So, partial pressure of A, partial pressure of B, both will be important when you look at the overall rate expression. So, basically the B is the collision between the molecules, right, whether B is colliding with itself or B is colliding with A in the gas phase, and then comes to the A adsorbed species and then transform into a product, which is shown here something like that, right here. So, your A is this reactant molecule. So, this adsorbs on the surface, B may also adsorb, right, but it is a very weak adsorption or weak chemisorption, but mainly this B comes to the adsorbed A star, right. So, onto this, and here it becomes a rate determining step. So, this transforms it into a product and that desorbs. So, here you can say it is not like A plus B, A B star, it could have been A P star also, right. That is the product species may adsorb on the surface and then it detached from the surface. So, there can be various kind of postulations when you devise the mechanism. So, here it is directly that A adsorbs here and immediately it releases from the surface in the form of a product molecule, right. So, this is what is shown here. So, reaction rate depends on the partial pressure of B, as it is mentioned here, right, dependent on the pressure of B P B, and the surface coverage of a theta A, right. So, but theta A will be depending on the partial pressure of A also, because the you know that rate of adsorption is proportional to the partial pressure and the concentration of the vacant site, that is the concentration of the catalyst or metal species which is present on the surface of a solid, right. So, this is main in the case of adsorption, because if the more partial pressure of A, but if it is on the surface of the gas on the gas phase, there will not be any chemical reaction, right. The reaction is only when this A adsorbs on the surface and then B can interact with that, right. So, we assume here that the B and the product do not competitively bind for the surface sites with A. So, another mechanism or the another mechanism can be devised based on this also, right, that B is also adsorbing, but it is a weak adsorption. So, generally the species, as I said last time also, the species which does not adsorb on the surface will not appear in the denominator of that rate equation, right. So, or in other words you can say it is weakly chemisorbed. So, weak chemisorbed, right. The species which is strongly adsorbed, it will appear in the denominator and that affects the rate, right. So, now as you have seen here, for this kind of reaction your rate will be given by the concentration of the adsorbed species A, which is this theta A, and the partial pressure of B. Just like in your homogeneous elementary reaction kinetics, the concentration of the reactant species, right. So, here the concentration of adsorbed species A, right, which is your theta A, something like A star, right, and this is the partial pressure of the B, which is mentioned here. So, now you have to find out theta A, right. So, theta A we have already done this last time. So, you are writing that the step which is fast, that will be at equilibrium, right, that is adsorption equilibrium. If you are writing this step something like here, then if I am saying that this is not rate controlling. So, this at equilibrium rate of forward reaction is equal to rate of backward reaction, right. So, that is this is simply your adsorption of A. So, one can very easily write down the expression for this, right, which is proportional to the concentration of partial pressure of A times the fraction of the vacant side, right, and other side it is just the desorption, because if it is reversible it will be desorbing from the surface, then it is simply the fraction of the surface which is already covered, which we have already seen last time. So, one can very easily substitute this value of theta A and also you know the side balance. So, here there is no question of side balance, because only A is adsorbed on the surface. So, just theta A plus theta V is 1, because other species are not adsorbing, right. So, for this case this concentration of adsorbed species or fraction of the surface adsorbed by A plus the vacant site is equal to 1. So, one can very easily write down the expression and I will just show that little later again. So, what we have postulated from this, so because this is k into P b and theta A is this thing basically k P A over 1 plus k P A, which we have done in the Langmuir adsorption isotherm also, right. That is at equilibrium the rate of adsorption is equal to rate of desorption. So, small k adsorption times partial pressure of A, right, times 1 minus theta A is equal to simply k desorption times whatever the fraction of the A which is already adsorbed on the surface, right. So, that is desorption is proportional to the concentration of the species which is already adsorbed. So, theta A, right. So, one can solve this and finally, it is this expression which has been substituted. So, now if you look at this rate equation, where we have said that this is the surface reaction rate determining step and rate was determined by this. So, one can very easily postulate from here that this rate is always first order with respect to the partial pressure of B, this, right. So, as you increase the partial pressure, the rate will increase from this expression, right. So, it means if you have done experiments or if you want to verify the model which you have postulated is correct or not, you can do the experiment in such a way where the partial pressure of A is kept constant and you have varied the partial pressure of B, right, keeping all else constant. All else constant means say rate calculation will be from your conversion versus W by F A naught graph. So, when you do the kinetics or when you generate the data for your laboratory experiment, then the data will be generated like this, right, and you will have a data, and as I advised last time also we should look at the low conversion data, less than 15%, not more than 20% something, but desirable is within 10%, because it is a differential reactor assumption, right. And you have to make certain assumption, but the equation says plug flow condition need to be maintained, right. So, you have to look at the height of the catalyst bed and the size of the particle also, right. So, L by dP it should be more than 50, generally for a plug flow you should not have any axial dispersion, right. Same thing for you have to avoid the radial dispersion also, right. So, radial dispersion again it means you have to look at the diameter of the reactor and the size of the catalyst particle, right. So, there are several theories. So, generally rule of thumb says that if diameter of the reactor divided by the diameter of catalyst is more than 20, you are safe, right. So, there will be negligible radial dispersion. So, it means you are closer to a plug flow model, right. And then isothermal condition you have to maintain, if it varies the endothermic or exothermic reaction, then temperature may vary. So, isothermal conditions also need to be maintained, and there you can add enough quantities of the inert material, right, to dissipate the heat like silicon carbide, right. So, some heat transferring material which can whatever the heat generates should be dissipated uniformly, right. So, these are certain experimental guidelines one can control and make the ideal condition for the kinetic study. So, here which is your conversion versus W by F A naught when you do. So, you can have the slope as I said, and you get minus R A, rate of reaction, which is written here. So, experimentally when you are doing this, you need to find out the parameters k, k, p. This is the meaning of model discrimination, when you are selecting 4 or 5 models and identifying the best model based on the regression technique, right. Some simulation package can be used for this purpose, and you minimize the error between experimental and theoretical, right, that is called objective function. So, you square that, because sometime error may be positive, sometime it may be negative. So, you just square it, so that all the time error is positive. You minimize that error, and then one can evaluate the model's parameter and see the error for each model, and where you have minimum error you can say that that model is closure, right. So, under certain constraints, again that constraints need to be defined. So, optimization of these model parameters can be done, right, because sometimes the different combination may come to the same result also, right. So, you need to look at the constants of the parameters of this equation, right, and under those constants you can just optimize the parameters, right. So, just like if you write k is equal to k 0 e to the power minus e upon r t Arrhenius equation, then the k is depending on e and k 0. If I put here minus r a is equal to k c a to the power n, suppose the rate is written like this, right. So, this k is a temperature dependent term which will be k 0 e to the power minus e by r t, right. So, it means the rate is dependent on temperature as well as on concentration, right. So, and if you n is also unknown, then this n k, right, or n k 0 e, these need to be determined, and there may be a lot of strong interdependency between these parameters. So, it means if you get some value of n is equal to 10, that is not right, right, n is equal to 100, not possible order of reaction, right. So, it means you can define some parameter constant for this n, that n should not be more than 3, something like that, right. And same thing for activation energy, if you are looking at kinetic control reaction, the activation energy should be high, right. So, more than say 20 kilojoule per mole. So, one can put that constant, right. So, under these conditions one can regress the data and find out the error function and model. So, that is the meaning of model discrimination, and then select the best parameter and look at which does it match with the experimental result for rest of the set of the data, right. So, that is how this kinetic data are generated and model parameters are evaluated. So, here what the conversion versus W by F A naught, if you use this data, then make it clear that this is at one partial pressure, if you are looking here this effect of P b, right. So, because you are saying that rate change something like, suppose here I am saying linear dependency. So, it means minus R A versus P b, it is this, right, but under when the partial pressure of A is constant, right. So, if you change the molar flow rate of A, right, then partial pressure is changing, right. So, you have to adjust either by using some inert, or you just make the total pressure of the system constant and then change the partial pressure of B and then add inert accordingly in such a way that the partial pressure of A does not affect the rate, right. And since you change the flow rate, so your W by F A naught may change if you have same mass of the catalyst inside the bed. So, again you need to readjust your mass of the catalyst also, right, and that is again under the constants as I said before, that mass transfer should not control the rate, it should not affect, right. So, your velocity, linear velocity across the bed should always be higher than whatever the minimum flow rate you have decided, superficial velocity, right. The mass transfer has to be eliminated because these are the kinetic parameters, right. No effect of mass transfer, no effect of internal diffusion in a pore of a catalyst. So, you need to identify. So, as it is mentioned here that the reaction rate is dependent on pressure of BPB and the surface coverage of A. So, this is what your theta A, right, and we devised this thing. So, first order with respect to B, that is keeping the partial pressure of A constant, and one can postulate it experimentally, and that is why one can say that B is not in the denominator, because rate is always increasing with the partial pressure of B. So, it is not adsorbed on the surface, right. And the meaning again is that K A, adsorption equilibrium constant, right, which is again related to heat of adsorption, right. If you have done some TPD studies, right, or temperature programmed studies, you can find out the heat of adsorption, right, delta H adsorption. So, and then from the thermodynamics one can calculate this equilibrium constant K, right. Some want of equations can be used here, right, d over dt of ln K is equal to minus delta H upon R T square, right. So, one can find out this equilibrium constant because delta H is known now, right. So, this delta H adsorption or K, either you say this or K heat of adsorption or equilibrium constant for A, if this is small, right, either or P A is small. So, I am talking these two terms here now, right. This is your equilibrium constant for adsorption and that is related to your delta H heat of adsorption, right, because from heat of adsorption you can calculate that K A, right. So, this either K A or P A. So, for small values of K A P A, if you look at here, then this one is larger compared to K A P A, right. So, in that case your K A P A is much more less than 1. So, K A P A much more less than 1, and in that case your rate becomes simply K times K A P A P B. So, this is basically capital K, just a minute. So, for this case your rate here, this denominator term, because this value is much more less than 1, when your either K is very small, right, or P is very small, or the combination of these two is very small compared to 1. So, this is neglected. So, your rate is simply K times capital K times P A P B, and that is the term which is shown here. So, this is capital K adsorption equilibrium constant, right, capital K A P A P B, right. This will happen at low partial pressure of A or if heat of adsorption is very small. So, this K is basically a thermodynamic parameter, right, and will depend on the temperature, right, as you know heat of adsorption change. So, the rate is first order with respect to A in this case. So, at low partial pressure of A, what I mean to say here, right, at low partial pressure of A also the rate is proportional to the first order, that what we have seen yesterday also for the Langmuir-Hinshelwood case, right. The second case, when this value, this capital K A, which is your adsorption equilibrium constant here, capital K A, delta H adsorption is large or P A is large, then this denominator K A P A, that will become much more larger than 1. So, you can neglect 1 in that case, right, and then this K A P A gets cancelled, right, and your rate becomes something like K times P B, right. Just it is depending only on the partial pressure of B independent of the partial pressure of A, that is at high pressure of A, right. So, it means if I have the experimental data, so one can very easily postulate the mechanism by doing the experiments, right. So, your minus R A versus P A, that is one set of data, when P B is kept constant, the data went like this, right. So, at high partial pressure of B, it is independent of this, right, P A, right, and at low partial pressure it is changing linearly, whereas for P B if you plot. So, P A or P B if I look at here, then it will always be something like this, right. So, effect of partial pressure of B is like this, effect of partial pressure of A is like this. So, one can postulate that with B, so B is not appearing in the denominator because it is not decreasing the rate, right, where A at high partial pressure of A, the rate becomes a constant value. So, it means something is there that A is absorbing on the surface, right, and at when the pressure is very high or concentration is very high, then this rate becomes independent of partial pressure of A. And suppose I had a square term in the denominator, it will go like this, right, similar term what we have seen last time. So, the basic idea, the question may arise that how do we postulate this mechanism? What we are postulating here, how do we confirm that? You can confirm by carrying out the experiment, right, or you can confirm by doing some simulation, molecular simulation, right. Naive functional theory or ChemCAN, these software tools are available nowadays to confirm them, right. Bond energy data are available which can talk, yes, when you have a gas molecule and this reactant molecule and this is the metal precursor platinum, there will be the adsorption, right. Say one can easily say hydrogen strongly chemisorb on platinum, right, oxygen can chemisorb on silver, like that, right. So, means these theories are already well established, or can be the further experiments can be done like this characterization technique by which one can identify that whether this kind of adsorption is possible or not. And this is what the theory also behind how to select a best or most appropriate metal for a given reactant species, right. So, rate is here in this case if you look at it, seems to be a 0 order with respect to the partial pressure of A, independent of the partial pressure of B, what you call 0 order reaction, right. So, it means the competitive adsorption of the product can complicate the kinetics. So, sometimes it may happen that A is adsorbing, B is adsorbing and the product may also adsorb. Right now, I have not talked anything about the adsorption of the product, right, but it may happen that the product which forms during the reaction, it adsorbs on the surface of the catalyst and then further it desorbs. So, when it desorbs, it may just release the surface, that may be one possibility, that product species itself desorbs and comes out as a product, or it may react with some other reactant species and transform it into a second product, different product, that will be a kind of secondary reaction, right, and this may be an undesired reaction also, like in multiple reaction happens, right. So, if you look at the mechanism, so there may be more than 100 reactions possible, right, 100 possible reactions for one reaction, just like in a cracking more than 200 reactions have been identified, right, more than 200 products are identified and still several are yet to be identified, right. So, mechanism becomes very complex for these kind of hydrocarbon reactions and depending upon the surface of the solid. So, when you diagnose a mechanism, whether it is Eller-Riedel type or the Langmuir-Hinshelwood type, the approach is similar, right. You have to postulate the mechanism, right, depending upon some basic fundamentals of the chemistry, surface science, right, and molecular structure, and then you have to just give certain hypothesis, right. So, if you measure the reaction rate as a function of surface coverage, the rate will initially increase for both the mechanism. So, whether it is Eller-Riedel type mechanism or Langmuir. So, you could have postulated a Langmuir-Hinshelwood type mechanism also, right, where A adsorbs and B adsorbs and then these two desorbs, right, and transform to the product species. So, Eller-Riedel mechanism, it says that it is increasing with the partial pressure of A, right, and so it is increasing as the surface is covered by A. So, when the surface is totally saturated, then your rate will go like this, right, the R A is equal to K times P A times theta V, what we have written here, right. So, when the surface is completely covered, then effect of A is not there, right. So, Langmuir-Hinshelwood rate passes a maximum and ends up to 0 when the surface is covered by A. So, in the Langmuir-Hinshelwood hypothesis, the adsorbed species will appear in the denominator, right, because A is adsorbing. So, this appears in the denominator. So, it will finally come to a value which is surface is totally covered, right. So, in that case this the maxima rate passes and rate passes to a maximum and finally it ends up to a 0 when the surface is completely covered here, right. So, theta A star it is written here. So, that is the fraction theta A covered by A plus the vacant side is 1, right. So, when the theta A itself is 1, vacant sides are not there, right. So, this may happen when you have Poisson precursor, right. So, effect of Poisson precursor it will completely cover the surface, but it will not dissolve from the surface, right. So, that is the complete deactivation of the catalyst. So, the basic idea is that when you have a surface coverage something like this, what we have seen here, the species which adsorb on the surface. So, the partial pressure of A becomes important, right, because higher the partial pressure more will be the surface coverage, right. This is your theta A fraction of the A covered, right, and when the surface is totally covered, but when I am saying this theta A becomes 1, it approaches to 1 and this will approach to 1 when this number K A P A and the denominator number K A P A is larger. So, ultimately this becomes 1. So, R is simply K B what you have seen, right, partial pressure of B. So, it means you can presume that the A has no role now, right, already the sites have been covered, right, at very high concentration or high partial pressure of A, right. So, that becomes important when you postulate a mechanism, given mechanism. So, this Langmuir-Hinshelwood rate will go some kind of maxima here in terms of the partial pressure of A when you look at that, right. So, just again we have discussed the similar step, but for exercise A is adsorbing on some site sigma gives you some A sigma. So, a reaction which is here and now we are just assuming that the product also has some role on the surface. Generally we are so far what I have said is that A adsorbs which is a reactant species, B is also adsorbing a reactant species, but when they react together they can directly transform into product species, right. But what happens when this product also adsorbs on the surface, right. So, there can be a different kind of models of postulations of the that for a given reaction on a surface of the solid, right. So, A adsorbs on the surface gives you A sigma, B then A sigma reacts with the gas molecule which is your and gives you R sigma. So, basically this is your Langmuir Ehlers-Riedel type mechanism, because this is in gas adsorbed species and this is a gas phase and this gives you R sigma, right, not R plus sigma. The another possibility can be that it gives directly you some product R and the site is vacated, right. So, second there can be the multiple option which have been written here, a kind of models which may be possible, right, and depending upon the theory, right. So, A sigma it gives you the R sigma plus S. So, both are product and R sigma will dissolve. A sigma reacts with B in the gas phase and then again it gives you the R sigma and S, another step, right. Then it can also be A sigma reacts with another site on the surface, right. So, the mechanism which you see here it can be a single site or dual site mechanism. So, single site mechanism and second one is dual site mechanism. When a single site adsorption site takes part for chemisorption, it is known as single site mechanism, right. And when two different kind of sites take part during the reaction, it is known as dual site mechanism, right. So, it may happen sometimes, suppose you take a bimetallic catalyst platinum rhenium on alumina, or sometime you have just say some platinum on HZSM5, right. So, there are some metal function and some acidic function, right. So, certain reactions when you have bifunctional, sometimes we call it bifunctional catalyst. So, the catalyst metal part may have some role, it may promote your hydrogenation activity, say platinum here, right, or dehydrogenation activity, but the acidic side it may do the cracking job, right, they promote the cracking reaction, right, or some isomerization, hydroisomerization, right. In this case the platinum and the metal side and acid functions have two different. So, these are known as bifunctional catalysts, or similarly there can be a multifunctional catalyst also, where you have certain promoters which can remove the coke from the catalyst or which can reduce the coke on the catalyst, right. So, the active site in a catalyst, we are talking in terms of these or whatever the acid sites of the support, right. So, when I am saying that the adsorption is happening on some site, it means those active site, right. Those active site means on the metal surface there is a platinum which is dispersed, right. There is some kind of rhenium which is dispersed. So, some gaseous species may have the more chemisorption tendency towards the platinum side. The second kind of gas species may have a chemisorption towards the alumina side, it may happen, right. So, these kind of, when I write it something like this, that A plus S1 gives you AS1, right, and B plus S2 gives you BS2, something like this, a dual kind of site, two different kind of sites are available on the surface of the solid, right. And then these two AS1 plus BS2 react and they give you RS1 plus SS2, something like this, right, where R and S are your product. So, reaction is something like this, A plus B over a catalyst transformed to R plus S. So, this R S1 now will dissolve and giving you R plus S1, site is free, right. So, I will write these small concentration here sites in terms of AS1 if I write, just to avoid the confusion between capital S and small s. So, small s is your some site, right here. So, this R S1 will give you R plus S1 and S S1 will give you S plus S1 S2 SS2 S plus S2. So, these finally these sites are vacant, right. So, two different kind of sites or a bifunctional catalyst which takes part during the with bifunctional catalyst on which the reaction takes place, right. So, in that case this kind of reaction mechanism is basically a dual kind of site, dual site mechanism. Two different kind of sites are available on the surface and then the reaction takes place, right. So, that is one important aspect when you have a bimetallic catalyst or bifunctional catalyst, but when you write a site balance, you can write site balance for S1 type of site, you can write the site balance for S2 type of site, you know what is the percentage of platinum is incorporated and what is its dispersion, what is the concentration of rhenium is added, what is its dispersion. So, concentration of these active sites are known, right. So, the site balance for S1 type, site balance for S2 site, and then you can write the same expression what you have derived before, right, similar expressions, not same, right. So, this kind of mechanism is a dual site mechanism. So, it means when A is adsorbing, B is also adsorbing on the site, right, and the or then also it is a kind of that A is adsorbing on one side AS1, B is adsorbing on a second side and then their reaction takes place, right. And when the something like this also we are said here that it is a sigma same side, the A is adsorbing, B is adsorbing. So, two reactions are taking place on the similar site, right, and one can postulate the rate equation. So, what I have shown here, these can be the possibilities during the reaction or mechanism postulation. So, just to look at that how the species which is adsorb on the surface of the catalyst, how does it affect the rate, right. So, as I have already told you that the species which adsorb will appear in the denominator. In one way you can say that the species which is strongly chemisorbed will appear in the denominator, right. So, this suppose you have the expression like this where A sigma gives you R sigma, some adsorbed species A plus sigma transformed into A sigma and then A sigma is transformed into R sigma. So, again this is a kind of a surface reaction, because this reaction is taking place on a surface of a catalyst, right, adsorbed species. So, that is why this is known as surface reaction. So, rate of forward reaction now it is simply the surface reaction rate constant times the concentration of the sites which are covered by A here, right, theta A. Rate of backward reaction, desorption of R sigma can also be possible. So, backward reaction rate is K minus S times the concentration of the species adsorbed by R, right. So, when these two are at equilibrium, just like as I said earlier, the rate of forward reaction is equal to rate of backward reaction, or what you say in the pseudo steady state also, the net rate of formation of the intermediate is 0, right, that is in homogeneous kinetics you say. So, here this the meaning of equilibrium, what I am saying that it is a rate divided by its adsorption coefficient is k, that is the rate adsorption is very fast, it is a very fast reaction, not controlling the rate, right. So, this k s into theta a is equal to k minus s into theta r. So, one can very easily find out, because k s divided by k minus s is your equilibrium constant for surface reaction, right. So, k s is theta r divided by theta a, right. But remember, this will happen only when this is very fast, this is not controlling the rate. If this step rate controls, then your net rate of reaction will be written k s times theta a minus k minus s times theta r, right. So, when this is at equilibrium very fast, then your rate of forward reaction equal to rate of backward reaction. So, k s is equal to theta r divided by theta a, that is these sites which are covered by r divided by the sites which are covered by a. The second postulation, if a sigma reacts with another site, right, on the similar kind of site, this can be a different site also, as I said S1 and S2, that will be a dual kind of dual site mechanism, right. So, here it is on identical site. So, a sigma plus sigma, it transform into r sigma and s sigma, right, r sigma plus s sigma. So, in that case your again if it is fast and at equilibrium, so rate of forward reaction equal to rate of backward reaction. So, that is basically here, if you say k s times theta a, sites covered by a, times this is vacant site theta v, right, is equal to this whatever the minus of this k minus s times concentration of adsorbed species theta r times theta s, right. So, if this is at equilibrium, then your adsorption equilibrium constant for s is defined by theta r times theta s divided by theta a divided by theta b, just like you define your adsorption equilibrium constant in thermodynamics, right, the concentration of these species. Same thing in the case of, suppose it is a Langmuir type adsorption isotherm, a sigma which adsorbs, and then again b sigma which is again adsorbed, and then these two reacts and transform into the r sigma and s sigma. So, here again you can define k s which is theta r times theta s, these two adsorbed concentration divided by theta a times theta b, right. So, this there can be different postulations, and another one a sigma, and this is your L Aridyl reacts in the gas phase, transform into r sigma and s. So, k s again for this can be defined in terms of theta r. So, P is in gas phase, so it will be partial pressure of the gas here, right. So, P s and divide by theta a adsorb, and P is in gas phase, so partial pressure of B, right. And finally, another one can be a sigma gives you r sigma plus s. So, here k s is theta r times P s divided by theta a. So, it means one has to identify the reaction step and then define the rate, and then also decide which step is rate determining, the others will be fast or at equilibrium. So, here we have just shown that if they are at equilibrium, how the rate or equilibrium constant will be defined. So, for the desorption, because r is desorbing, so your r sigma will give you r plus sigma. So, desorption of r is the reversal of the adsorption of r, which we have already shown and discussed. So, forward rate k d times theta r, backward rate k minus d times partial pressure of r, and the vacant site concentration. So, basically I have already talked this r plus sigma is r sigma. So, here just shown in the reverse way, but otherwise because it is a reversible. So, the what you got before same here. So, k d into theta r is equal to k minus d times partial pressure of r times theta v, right. So, theta r can be calculated in terms of partial pressure of r times theta v, which is your vacant site concentration, divided by k d, and that rate of adsorption if you look at, right, that is equilibrium constant for adsorption will be 1 upon the equilibrium constant for the desorption, that is another thing. So, what is written here in terms of k d, right. So, 1 upon k d is your what you have seen earlier for the forward reaction, right. So, that is here, right. So, that is adsorption and desorption both are identical in that way, the r sigma which is written r plus sigma here, right, and I have not shown it here, but basically what I am saying that if I write R plus sigma is equal to R sigma, right, that is adsorption of R, and when I write R sigma is R plus sigma, that is desorption of R, right. So, equilibrium constant for adsorption is reciprocal of the equilibrium constant for the desorption of the same step, right. So, just to explain the terms here, an example has been taken for cumene, right, isopropyl benzene, which is one of the important petrochemical raw material and can be used for producing benzene and propylene, right. So, this is isopropyl benzene, a aromatic ring compound, right, transforms to benzene and propylene, right, over some catalyst, right. So, cumene C gives you benzene, I have just given B, benzene as B and propylene as P, right. So, mechanism which can be suggested based on the experimental data, some informations have been observed that propylene does not adsorb, because rate is proportional to the propylene partial pressures, right. So, propylene does not chemisorb on the surface, that is one thing. So, there are certain postulations which have been observed during the experiment, and now the mechanism is devised, right. So, the mechanism which is something like here, first cumene adsorbs on the surface of a catalyst and gives some adsorbed cumene, right, adsorption of cumene, this is the first step. Then this adsorbed cumene transform into some adsorbed benzene and the propylene which is not adsorbed. Directly the cumene and on the surface of the catalyst which is adsorbed transform into a benzene propylene which will go into the gas phase, and benzene which is some adsorbed benzene on the surface, and finally, this benzene desorbs and gives you the product benzene and the site is vacant, right. So, propylene does not adsorb. So, this is just an example problem to clarify or how to get the rate expression or finally get the model discrimination or identify the parameters of the model. So, rate laws can be defined for each step. So, a general rate law that net rate of adsorption of A, I am not saying that they are fast or at equilibrium. So, net rate of adsorption of A, right. So, for this is first reaction adsorption of A. So, rate of formation of this adsorbed cumene, which is nothing but rate constant for the forward side multiplied by the partial pressure of cumene times the concentration of the vacant side, right, that is the forward side. Reverse is C sigma transformed into this. So, rate is proportional to the concentration of the adsorbed cumene side. So, this rate constant times the partial pressure of cumene times the concentration of vacant side minus the desorption rate constant times the concentration of adsorbed cumene, right, that is net rate of adsorption of cumene which has been shown here, right. So, K A times the partial pressure of cumene times the concentration of vacant side, right, forward reaction rate. So, this is reaction in the forward direction, and this K minus A which is desorption rate constant times the concentration of the sites which are already adsorbed by cumene, because cumene is being desorbed, right. So, that is the reverse reaction rate. So, net rate is the just like in a reversible reaction for the homogeneous system you write. So, rate of forward reaction minus rate of the backward reaction, these are net number of molecules of cumene adsorbed, and when you say that this is very fast and at equilibrium, then this should be 0, net rate of adsorption is 0 at equilibrium, right. If none of this stuff is rate controlling, as I said before also, then you have to make the overall, that is at steady state net rate of formation of intermediate will be 0, right. So, here if the reaction is very fast and at equilibrium, one can write the rate of forward reaction is equal to rate of backward reaction. Similarly, for surface reaction, so second one is your surface reaction here. So, concentration in this is your forward side of the reaction will be proportional to the concentration of C sigma which is your adsorbed species, right, and reverse side this is depending on the concentration of adsorbed B like theta B, and the P is in gas phase. So, partial pressure of P, right. So, here it will become K S times theta C, the concentration of cumene which is adsorbed, minus reverse reaction which is K minus S times the concentration of adsorbed benzene times the partial pressure of propylene, So, this is net rate of surface reaction, and if I say surface reaction is rate controlling, this step will be written as the rate controlling, and other two will be written very fast, and these two will be at equilibrium, and then you can find out theta b theta c using these two, right. And net rate of desorption for the third one, desorption step here, B sigma, benzene which is adsorbed now will desorb. So, rate of benzene desorption is nothing but the rate constant in the forward direction times the concentration of the benzene which is adsorbed, theta b, right, minus the desorption step, that is this side. So, that will depend on the partial pressure of the benzene and times the concentration of the vacant site, right. So, this is written here. So, K d rate constant for desorption of benzene times the concentration of the benzene which is already adsorbed, because desorption will depend on those concentration, and minus K minus d which is the reverse reaction rate constant times partial pressure of benzene times the vacant site, right. So, any step can be rate controlling, right, and other rest can be assumed as it they are at equilibrium, right. So, one can postulate the overall rate. So, here we have just shown the different step case by case. So, first may be that if adsorption is rate controlling, as I said that model discrimination, right, and parameter estimation. So, you have suggested a mechanism. So, mechanism suggested is like this, the first step, hypothesize a mechanism based on some experimental clue, right, and then you had just written the rate expression, because assuming that each step is at elementary step, right, these steps are assumed elementary step of the reaction, right. So, and then now we are postulating that there may be three possibility, this system may be rate controlling, or this system may be rate controlling, or this system may be rate controlling, right, 3. So, either one is rate controlling or second or the third, right. So, you have to take 3 different cases. If one is controlling, then these two will be very fast and at equilibrium, right, and so on so on. So, you can develop the model and then finally evaluate the parameter. So, this is what I am doing here. So, the first one is the adsorption as the rate controlling step. So, if adsorption is rate controlling, then your net rate of disappearance of Q mean, that is the adsorption, right, adsorption is given in the first step here, right, because this is the rate controlling now. So, my overall rate of reaction will be given by this expression, right, in the first case. So, here partial pressure of Q mean is known parameter, but theta v is the concentration of vacant sites which is not known, you have to find out in some of known parameter. Same thing for theta c is not known. So, that can be determined by using these two, right. So, because they are fast and at equilibrium. So, this has been done here. So, rate of adsorption which is written here, now you can take capital K A out. So, this becomes P c times theta v minus theta c times capital K A divided by capital K minus A, right. So, this is basically 1 upon K, adsorption equilibrium constant. So, this is the equilibrium constant now, right. Rate of forward reaction divided by rate constant for the forward reaction divided by rate constant for the backward reaction, and that is the definition of adsorption equilibrium constant. So, basically this capital K A, small k upon K minus A, this is your capital K A, right. So, surface reaction, as I said, because this is rate determining, rate controlling RDS. So, for RDS this, the other two steps are at equilibrium. So, rate of forward reaction is equal to rate of backward reaction, or net rate of formation of that species is 0, net rate of reaction is 0 rather. So, K s times theta c minus K minus s times theta b times P p is equal to 0. So, from this one can find out the concentration of adsorbed Q mean, right. The surface sites which are covered by Q mean is theta c. So, that can be find out. So, whether you write theta c. So, theta c is represented as fraction of the sites covered by the Q mean, right. One can write C c also, concentration of the sites covered by Q mean. So, any definition can be used. So, theta b times partial pressure of this, because theta b times P p divide by this is again here K s here this expression which is written equilibrium constant is k small s divided by k minus s, right. So, that is adsorption equilibrium constant or equilibrium constant for surface reaction, right. Rate of forward reaction divide rate constant for the forward reaction divided by rate constant for the backward reaction. So, that is the equilibrium constant for this reaction, right. Same thing for the third reaction which is desorption. So, k d times theta b minus k minus b d times P b times theta b is equal to 0, because this reaction is again very fast and at equilibrium, right, or net rate of formation is 0. So, in that case again one can find out theta b. So, theta b will be simply P b times theta v divided by k d divided by k minus d, right. So, rate constant for desorption divided by forward rate constant divided by the reverse rate constant. So, that is your adsorption equilibrium constant or desorption equilibrium constant, right. So, equilibrium constant for desorption of benzene, right. So, one can write K d subscripted again b, right, for benzene. So, theta b is known, theta c which is written in terms of theta b. So, theta c can be calculated, because theta b is unknown here, right. So, theta and this is now theta b which is again here theta b is unknown, right, but you can write it in terms of total site balance. So, theta c is equal to P p times theta b. So, theta b is substituted like this P b times theta v, and the other two equilibrium constant K s and K d are in the denominator, right. So, the still you need to find out this theta v. So, let us look at the site balance, right. So, site balance you know that the cumene is being adsorbed on the surface, benzene is being adsorbed, but propylene is not adsorbed, right. So, the sites total number of sites if you say, right, fraction of the site if I talk 1, right, sigma of all theta I. So, that is 1, right. So, fraction of the sites these are theta c covered by C, fraction of the sites covered by B, and the fraction of the sites which are vacant, right. So, summation of all these will be 1, or in other words you can say the concentration of sites adsorbed by cumene plus concentration of sites adsorbed by benzene plus concentration of vacant site is equal to total concentration of the site C t, right. So, this is basically C c over C t, this is C b over C t, and this is C v over C t, what I have already discussed. So, one can very easily find out from this, because theta v is known now. So, minus R c which is net rate of disappearance of cumene, right. So, rate of disappearance of cumene which was defined here like this, right. So, you have defined in this form now. So, substitute the value of theta v and theta c and you get the expression here, right. So, K a times P c times theta v minus theta c, and all these terms are now known, right. So, substituted here in this. So, this is small k times P c times theta v and theta c is substituted already calculated. So, P p P b divided by K a. Now, this is equilibrium constant for the adsorption reaction, surface reaction, and this is the desorption of benzene, right, times theta v. So, you can further simplify this. So, theta v can be taken out. So, K a times theta v, and in bracket you have now P c minus P p P b divided by this other rest of the term, right. K equilibrium constant for the overall reaction, because what is your overall reaction? This is your overall reaction, right. C gives you P plus B. So, what will be K equilibrium constant? At this overall equilibrium constant which you get from thermodynamics will be simply the concentration of P times concentration of B divided by the concentration of C, right, and that is written there in terms of either right partial pressure. So, this is at equilibrium, right, equilibrium composition. So, which is written here K equilibrium. So, this term which is if you see there, that is nothing but the combination of all these rate constants here. So, P p P b, so P p P b which has come from theta c, if you substitute that, which we already done, and K a times theta b times P c is here P p P b P p P b, right, which is written here P c C b, divide by your third term C c, right, in the denominator, which is your concentration of C, and that has been just written in terms of combination of all these, which is K a, K s, K d, right, and the whatever in terms of the total or overall equilibrium constant for the reaction, right. So, the basic meaning of this is that because the overall equilibrium constant of the reaction is known to you from thermodynamics, right. So, and the term which is reported here in this, in the form of, because these are beyond equilibrium. So, when the equilibrium arrives for this reaction, this, suppose if I say 80% conversion. So, after 80% the rate of forward reaction is equal to rate of backward reaction for overall reaction, right. You cannot achieve more than that conversion, that is the meaning, right. And means for a given condition of temperature and pressure, if you disturb your equilibrium you can get more. So, for these kind of membrane type of reactors can be used, or some the molecular distillation type of reactive distillation what you call nowadays. So, these type of reactors can be used, but when you have the for a given reaction at a given condition of temperature and pressure, the equilibrium conversion can be, that is what written in terms of C E here, right, the concentration of E at equilibrium, right. So, that is, so when there is equilibrium, so these all are the concentration at equilibrium, which, so it means one can define the concentration at equilibrium or the conversion either way, right. So, these terms are just defining that the driving force, a kind of driving force which is required for a reaction to happen. So, if this driving force is not there or the great difference is not there, there will not be any chemical reaction, right. So, this gives you the idea that how far you are deviating from equilibrium, right. So, which is P c minus P b P p P b upon K equilibrium, and that is just talking, one can look at in terms of the P c, that is the concentration of C minus that at equilibrium when you define the rate, right. So, that can be just to check whether your, when the concentration of cumene reach to the equilibrium composition, there will not be any further conversion, right. So, that is what from thermodynamics one can find out, that what is the equilibrium conversion, and accordingly the conditions can be decided. So, your net rate of disappearance of cumene is simply now written K a times P c minus P p P b upon K equilibrium, and divide by 1 plus, which is the term here written in form of Langmuir-Hinshelwood, because theta v is known now. So, from this theta v is equal to 1 minus theta c minus theta b, substitute the value of theta c and theta b, and then you have the expression something like this, which is here in the denominator. So, 1 plus P p P b divided by K s times K d, equilibrium constant, and plus P b upon K d. So, this is the final rate expression for the disappearance of the cumene when adsorption of cumene is rate controlling. Remember, this is a one specific case or the rate expression which will say that the if adsorption is rate controlling, then it should depend on the partial pressure of C, that is cumene, it should depend partial pressure of B, it will be depending on the thermodynamic equilibrium constant, right, and what are the terms defined in the denominator of the equation, right. So, this will give you a kind of guideline that whether the reaction is rate controlling, right, or not, right, for a given conditions. So, if adsorption is rate controlling, our rate should match to this kind of parameter, right. So, there can be other case, second case, which is the surface reaction is rate limiting, right, and similarly. So, for surface reaction again you have to proceed all these steps during the reaction, right. So, I will continue it next time. So, thank you.